All right. Good morning, ladies and gentlemen, and welcome back to your least favorite class. No, I'm just kidding. That's April Fool's joke. We all know this is your favorite class. Come on. A couple of announcements really quick. So yesterday about MSOE moving from the traditional grading scale to now pass-fail for all classes. So this sort of administration made this decision for a variety of reasons, including, people maybe having limited access to online learning, or the online learning maybe isn't going as well, and this just gives a little bit more leeway for kind of the random situation that we're in. I sort of think there are good things and bad things about this. Good things in that, yes, I understand and sympathize with where they're coming from. I think maybe there should be a little bit more leeway this quarter, but bad in the regards that it really gives people a lot of room now to just kind of be lazy. So I hope that you will not adopt that mentality. There's not much that's going to change about the way my class goes. I'm still going to collect homeworks. I'm still going to give you a numeric score in your homeworks. I'm still going to run the exams as normal, give you a numeric score for your exams, so on and so forth. Just at the end of the quarter now, instead of receiving what would be a letter grade, you'll receive either a P for pass, an LP for low pass, or an F for fail. So a pass for my class will be a C or better, so more or less a 70 or better, and you will get a passing grade for the class. An LP is, for all intents and purposes, the same thing as a P, so a low pass and a pass are the same thing. So a low pass for me is a CD or a D, so that's 60 to 67 for a D, and 67 to 70 for a CD. So for all intents and purposes, an LP is the same thing as a P. You still got credit for the class. You're still making your way through. And then if you're below the 60% threshold, it's enough for the class, and it's enough just like normal. Okay, you don't get credit for the class. If this is sort of a class that you need for graduation, then you're kind of in trouble. All right, so that's kind of the way it's going to go. I'm going to keep doing the same thing that I'm doing. I'm going to proceed the same way, except at the end of the quarter, you're going to see either a pass, low pass, or an F. That you might see it as an NP, a no pass. You shall not pass. Rawr. I'm just kidding. So that's what that email relates to this class. If you have any questions, maybe I can try to answer some of them, but more or less, you probably want to see that email and maybe go to some of the resources that are laid out in that email. Okay, moving on. Homework 2 for us will be due Monday of next week, so make sure you get that in. If you have questions, I'll be responsive over the weekend. But we should be able to get through the material, all the material that we need to get through by maybe not the end of today, but for sure by the end of Friday. Okay, so that homework should be on track. You should be able to get that done to hand in at the beginning of lecture on Monday next week. All right, so any questions? Any questions? We wake out there, maybe not. It's hard without, like, some banter back and forth, some other people interaction for me. Makes me go crazier faster. All right, so let me pull up my notes here and we'll get into things. All right, so I'm going to share my screen here and kind of round out the last of the classical lamination theory notes and sort of summarize what we were talking about last time. So last time we were talking about special laminates, and these are laminates that have stacking sequences that are for some reason special. We could have a symmetric laminate where each ply is a mirror about the midplane, anti-symmetric, unidirectional, cross-ply, all these sort of classifications. And the stacking sequence for these particular laminate, if they fell into one of these particular special categories, we could immediately eliminate or simplify the calculations of the A, the B, and the D stiffness matrices. So these are the laminate stiffness matrices. And so we talked about and showed one example with sort of a symmetric laminate and how we might see that calculation proceed and go forward. So if there's some of these symmetric characters or these special characters of the laminate, the calculations of these A, B, and these D matrices proceeds a little bit easier. Okay. Now, last thing I want to do is I want to just quickly go through this example. We sort of went through an example already without numbers, but I want to go through an example with numbers here just so we can bring it home. And this is going to be similar to what you have for homework problem number 1 on homework number 2. Okay, so let's say you're given the principal in-plane stiffness matrix, here this matrix Q, for a certain glass epoxy lamina, and you calculate it to be something like this. All right, remember that you could calculate this from fiber volume fraction, material properties of a lamina that you created. Okay, so remember you can calculate E1, E2, nu 1, 2, so on and so forth, and those feed into the S matrix, which you can then invert to get this Q matrix. All right, so that's something you did on homework 1, so hopefully you're sort of comfortable with that now. All right, so given these values in our in-plane stiffness matrix Q, we want to calculate A11, B11, and D11 entries for a laminate stack that's 0, 30, 30, 0, and assuming that each one of the lamina in the stack is 2 millimeters thick. All right, so I'll come over to the writing pad for just a second, and then we'll throw it back over to the PowerPoint slides to sort of just run through it quickly. Okay, so here's the example, and I'll switch over here in just a second. Okay, we have an example, and the picture that you should sort of have in your head is going to look something like this. You've got a laminate stack. It's 4 layers thick. Okay, and the general orientation for this guy is going to be 0, 30, 30, 0. And then each one of these is 2 millimeters thick, each one of the lamina. So the total thickness here is 8 millimeters. 8 meters, whew, that'd be a thick laminate. 8 millimeters. All right, so this is what you should be thinking of when you think of this particular laminate. Maybe I should have included that picture on the slides. All right, so let's throw it back to the slides really quick. And I'm just going to run through the solution here. The solution is available in the notes. I'm going to kind of go through this pretty quickly. If you want to sort of take a look at the solution in a little bit more time with a little bit more clarity, I would advise you to do that. I'm just trying to like keep the pace up a little bit here so we can go through it. All right, so here's sort of my handwritten solution. We're going to go starting kind of top left with just generally defining off-axis values of the Q matrix, right? So the first thing is you're going to need the stiffness of the 30-degree layer to proceed with this problem. So the first thing you need to do is you need to rotate the in-plane Q matrix to get what is the Q matrix for the 30-degree orientation. Okay, so this is again something you did in your homework or should have done in your homework for homework number 1. And to obtain that, we do T inverse with the value of theta is 30 multiplied by Q multiplied by T star for theta is 30, where you can define these transformation matrices using the rotation angle 30 degrees to define these guys. Okay, so go back to your equation sheet. Remember that M is cosine theta, N is sine theta. We can use that to define the T matrices here for our proper transformations. Okay, so we'll have to invert this guy, this T matrix, to execute appropriately. But if you go through this, you end up with a Q bar matrix, which is the stiffness matrix of the 30-degree oriented lamina, which looks something like this. All right, so notice now that it's still symmetric, but we have non-zero entries in the sort of upper diagonal or the upper triangle in this particular guy. All right, so once we've established what the Q-bar matrix is for the 30-degree orientation, we're sort of ready to proceed with this particular sample. Okay, so we know we only have 0 layers and 30-degree layers. The Q matrix for the 0-degree layer is what was given in the problem here. Okay, so if it's 0 degrees, it's in principal material coordinates. And then here, the Q matrix for 30 degrees is this particular guy. All right, so now we're ready to calculate our A matrix, and generally the equation for this particular A matrix is going to be Aij is the summation from K is 1 to 4. We have 4 layers here of the stiffness of the kth layer multiplied by the general thickness of that layer, Zk minus Zk minus 1. Okay, location of the bottom minus the location of the top of that laminate. All right, a note that we'll make here, the total laminate thickness is 8 millimeters. And these are our general definitions for these Z values. Remember, I'll pop over here to PowerPoint for just a second. Remember, we define our midplane as sort of the location of z equals 0. And so we would say here to the bottom, this is z0. And here this is what would be z1. Here's z2. Here is z3 and z4. Okay, so just defining from the center of the laminate stack to either the top and bottom of the various lamina. I know it feels like I'm beating this ABD thing to death, but it really is the foundation for pretty much what we're doing the rest of the theoretical portion of this class. Okay. All right, so here we define our Z values, and now we're just ready to plug in. So the AIJ, since we have 4 components, becomes QAIJ of the first layer multiplied by thickness of the first layer plus QAIJ second layer times thickness of the second layer, so on and so forth. Okay, and we'll note here that the thickness of each layer, ZK minus ZK minus 1, is just 2 millimeters. All right, so that's pretty obvious to see. And our QIJ1 and QIJ4, so this is the stiffness matrix of layer 1, stiffness matrix of layer 4, is the stiffness matrix of the 0 degree orientation, which was given to us in the problem as just this particular guy here. All right, so we know that's given to us in sort of the principal material directions, and that is for theta equals 0. Now, layers 2 and 3, we're going to use the stiffness matrix for when theta is 30 degrees, all right, which is this guy here that we calculated over here. All right. So proceeding on, you're going to end up with something that looks like this, pulling the 2 millimeters out for each one of the individual layers. And then we have 2 contributions from stiffness layer of the 0 direction, 2 contributions from the stiffness in the 30 degree orientation. And we move through with our calculations, plugging in the numbers here. So if we're looking at the 1-1 entry, we're going to take the 1-1 entry of Q for theta equals 0 degrees. And we see up here that that is 73 GPa. And then here, the 1-1 entry for the theta is 30 degrees matrix. We see from our previous calculation that that here is 72.1. And that gets us a value for the A11 matrix, 580.4 GPa millimeters, or if you convert to Pascal meters, which is common, it's 580.4 times 10 to the 6th for A11 entry. Okay, so this is kind of going through a full-blown application or full-blown calculation with numbers. Bij, all Bij are 0, this laminate is symmetric. All right, so that's easy. So B11 here is 0, and that's because we know the special character of this particular laminate. All right, lastly, our D matrix, here's sort of the full calculation. Again, the same idea holds. Don't forget your 1/3, contributions of the stiffness from each of the individual layers, multiplied by these locations of the laminates, all to the 3rd power. So again, we go through, we know all these individual values, including what would be the QIJ entries now for the 0 degree orientation, 30 degree orientation lamina. Plug all the numbers in appropriately with cubed values appropriately, and you'll end up with a D11 of 3110 Pascal meters cubed here. Okay, so again, I want to give this example with numbers because it's similar to what you got going on for the first homework problem in homework number 2. All right, there we go. How we doing? We awake? Got the coffee going? I got my Perrier. I'm fancy. I drink boring regular water when you could drink sparkly water. Okay, so with that said, I'm going to move in onto the next set of notes. And that is, we're going to introduce the idea of laminate engineering properties. The next set of notes is laminate engineering properties. All right. Now, we've calculated or gone through all these steps now to calculate things like the A matrix, the B matrix, and the D matrix, right? And those matrices kind of define the constants that sort of make up the relationship between applied loads that we might have and strains and curvatures that develop, all right? But it's not really intuitive to discuss material properties in terms of like A, B, and D matrices. Okay, so if someone fabricates a laminate, you're not going to walk up to them and be like, "Hey, man, what's like the A11 value for that guy?" All right, it doesn't really make a whole lot of sense. So instead of talking about properties of the laminates being like A11, B26, whatever, you probably want to talk about like what is the stiffness or the elastic modulus of this particular material if I load it in a certain direction. Okay, so given a laminate, we would like to sort of talk about or describe the way that the laminate behaves using typical engineering properties. We'd like to describe its behavior with typical engineering properties. So think about things like the modulus or Poisson's ratio. So like modulus should come to mind, or Poisson's ratio should sort of come to mind. All right, these typical physical, physically interpretive contexts. All right, these concepts. All right, modulus, Poisson's ratio. So let's sort of take a step back in our Wayback Machine, back when we had the outside times, and we'll talk about what you talked about in ME3005. All right. So what would happen if we wanted to do or sort of describe these things for an isotropic material? All right. So for isotropic material, that's pretty straightforward. You would kind of run a test. And that test might look something like this, where you have some coupon. I don't know, let's make it rectangular for now. And to this guy, you're going to load it here with some load P, load it here with some load P. Okay. And what's going to happen? Well, that thing's going to elongate and you're going to create stress. All right. So this will give you a stress, which is the load over the area. And if this thing sort of like elongates during the test, which it might, so this is delta plus L, right? The displacement plus the original length. Then you're going to get a strain that is something like delta over L, right? Then your elastic modulus E is simply the stress divided by the strain, all right? This gives you sort of an engineering constant, the elastic modulus, described in some physical things that you did, right? So you applied some stress, there was some strain that resulted, you measured those things, and away you went. All right, so for isotropic materials, that's pretty straightforward. That's pretty easy. All right, but for composites, it's more complicated, right? So if you had sort of a laminate material, so let's consider a laminate, where maybe, again, you have like a rectangular coupon that looks like this. But it's a laminated material, so you have maybe multiple layers of that particular material in sort of this laminated fashion. All right. So now if we pull on this guy in this direction with a force per unit length, which might be something like Nx, right? This is force per unit length. Then the response is complicated. The stress in X is not just Nx over the cross-sectional area. All right, we know that it's more complicated than that because the stress distribution is different in each layer. Okay, it's not necessarily that value, since stress varies in layer. And the strain is not just whatever your displacement is over the original length. We know that when we pull on these laminates, there can be shear strain that develops, there can be curvatures that develop, there can be all sorts of things that develop. All right. So you can develop shear strains and curvatures from axial loading. So it's much more complicated. Okay. So we have to like talk about what strategy we might employ to maybe discuss something like, all right, well, what is the stiffness of this guy in this particular direction, given a certain assumption about loading and cross-sectional area and all this sort of stuff. So we need a different strategy is the point. Need a different strategy. All right. So let's talk about, for us, what that strategy might look like. And let's sort of work our way a little bit through what the math might look like to get to our ultimate final location. All right. So how might we do this? Okay. Well, let's assume we know our ABD matrices. Okay, so we know the laminate stacking sequence. We know the stiffnesses of each of the individual lamina, so we could construct the AB and the D matrices. All right, so let's assume we know that, and let's assume we apply some known forces and moments. Which in this class we call N and M, where these are vectors of nx, ny, and ns, and then m is mx, my, and ms. All right, so remember we've kind of talked about these. All right, then we can discuss things like the relationship between loads and strains. Okay, so the following strategy might occur. Here's our strategy. Step number one would sort of be to determine what the strains and curvatures of the laminate that result would be. Okay. From previous lecture, we know that the relationship between the forces and moments that we apply, N and M, are related to the strains and the curvatures that develop through the stiffness matrix A, B, B, D, multiplied by the midplane strains epsilon 0 and the curvatures kappa. All right, so we know this. If we actually want to determine what strains and curvatures might develop if we have applied loads, then we simply invert this to determine what the strains would be. So if we want the strains and the curvatures, we could invert this to get epsilon 0 and kappa here equal to this ABBD matrix inverted multiplied by the loads and moments that we may apply. All right, so that's sort of step number one, is to determine what the strains and curvatures are that might develop. All right, so step number two is to come up with some expression for the stress, is to estimate stress applied by averaging N and M in some way. All right, so if we could come up with some like average stress that we might be applying, then we might be able to relate the strain that we can sort of determine using this inverted ABBD matrix to the stress that we apply, which is like this average stress, to determine things like the modulus, all right, which is a relationship between stress and strain, right? So we will employ the mean value theorem. It's so mean. To give sort of estimated stresses. And we will show that we can do that by writing something like the mean stress in X, which we'll call sigma X bar, the mean stress in Y, and the mean shear stress, which we'll call tau X Y bar, or you may see it as sigma S bar, is equal to what would be the applied loads Nx, Ny, and Ns, all normalized by the thickness of the laminate 1 on H. All right. So here, these would be average stresses, and this would be applied loads normalized by thickness. All right, where H is the full thickness of the laminate. And we will sort of show how this comes to be. All right, so if we then have some average stress that we're applying, and we can sort of estimate the strains and curvatures, then lastly, we'll say that we can approximate the laminate engineering properties with these strain curvature and stress values to sort of come up with what we might say is sort of an approximate laminate stiffness or an approximate laminate Poisson's ratio. So ergo, a mean modulus which might be something like E bar X approximately equal to what would be this mean stress calculated from the mean value theorem divided by, let's say, the strains which might develop in the X direction. Okay, so that's the general strategy. So let's go ahead and work our way through this. So step number one would sort of be coming up with these strains and these curvatures from applied loads and stiffness matrix. So first, we're going to talk about the laminate compliance matrix. All right. This laminate compliance matrix is just the inversion of the laminate stiffness matrix. So remember, we had the relationship between the applied loads. Here would be N and M, these applied loads in moments, which is AB, B, D. These stiffness matrices multiplied by the strains that develop, epsilon 0 and kappa. I always have a problem with that, like kappa. I never really know how to like draw that. I like want to just like put a normal K, but I have to like distinguish somehow. So I like put this curly Q on it. Like, I don't really know what I'm doing. Okay, try my best. All right, so this is our general relation. And we said that this full matrix here, this is our laminate stiffness matrix. All right, so we can invert so that we solve for the strains. And that would leave us with the strains and curvatures. Here's my Busta Kappa Kappa again, my favorite fraternity. Will be the inverse of AB, BD multiplied by the loads and moments we apply. All right, so this is pretty straightforward, calculating the strains and curvatures from the applied loads. All right, this here we would call the laminate compliance matrix. And usually it is written with lowercase a through d. So we use uppercase a through d to talk about the stiffness. And we'll write here that this laminate compliance matrix is often written as lowercase a, lowercase b, lowercase c, and lowercase d. Okay? So we'll make a note here that generally the B matrix, which is, remember, all of these are 3x3s. So let's be clear about that. And we'll here note that it is not necessarily the case that little b and little c are equal to each other. Okay. So it was a little bit strange that when we talk about the stiffness matrix, that generally the B matrix, which occurs in the upper right and the lower left sort of quadrants of the 6x6, end up being equal. But when we invert, because of the inversion properties of matrices, that the upper right and upper lower quadrants are no longer necessarily equal to each other. All right, so we have to be very careful about what's occurring in this situation. All right, so this is sort of your laminate compliance matrix. It's the inversion of the laminate stiffness matrix. So you're now probably getting to a point where you're seeing why we're going to have to start doing a lot more MATLAB in this class. All right, when we're talking about making 6x6 matrices, using 3x3 matrices, and then inverting them and relating that to applied loads and all this sort of stuff, man, it's about time to not be doing things by hand anymore. All right. So if we want to write full-blown shorthand notation relating strains to applied loads, we can write that the strains and curvatures that result from applied loads are this compliance matrix A, B, C, D multiplied by N and M, the loads that are applied. All right. Where we know this general relationship to be true. All right. So that's what we got going on generally. If we have a symmetric laminate, things sort of shake out and things become a little bit more clean. Okay. And that's because when we have a symmetric laminate, the B matrices of the stiffness matrix kind of go away, the capital B matrices. All right. How are we doing? Any questions right now? Nope. I'm just continuing to talk to myself. Okay. Okay. So this is generally the relationship between strains that might develop if we apply loads to our piece. All right, this is the general case. Oftentimes, though, we make simplifications known special laminates, right? So for a symmetric laminate, we just talked about this, that the B matrix is equal to 0. So the total stiffness matrix ends up looking like the loads and moments that we apply equal to the A matrix times 0 times 0 times the D matrix multiplied by epsilon 0 and kappa. So with these zeros in place, we can see that there is decoupling of the curvatures from the applied loads N and the strains from the applied moments M. So this decouples matrix. Where generally, if we look at these equations, we'll have that N is equal to A times epsilon 0 and M is equal to D times kappa, right? So there's no relationship between strains and moments, and there's no relationship between curvatures and applied loads N. All right. So then can then calculate inversions easily. And because we can sort of decouple the applied loads N from whatever curvatures we might have and the curvatures from the moments, we would end up with something like, again, N equals A times epsilon 0. Easily, we can see that the inversion here is something like little a times N is equal to epsilon 0. Also, since the moments applied are the D matrix times the curvatures, the inversion here is little d times M equal to kappa. All right, so this is specifically for compliance relationships to get strains. All right, so no longer do we have some big 6x6 that we worry about. Here, these are just these guys here are 3x3. These guys here are 3x1. And these guys here are also 3x1. Okay? So instead of having the big 6x6 mumbo jumbo nonsense, if we have a symmetric laminate, we can sort of decouple these things, break them apart, and make our lives a little bit simpler by working sort of in a 3x3 space rather than like a 6x6 space. Okay. My pen's been good today. It hasn't like crapped out on me once. I haven't run out of ink in my pen once today. Okay. So way back at the beginning here, we talked about our general strategy for ultimately coming up with laminate engineering properties. Strategy number 1 was to define strains and curvatures from applied loads. Okay, so define strains and curvatures. We did that by discussing sort of the inversion matrix to get ourselves a compliance matrix, which will give us strains from applied loads and moments. All right, step 2 in our strategy is to estimate the stress applied by averaging the loads and moments that are applied to sort of give us an average stress over the laminate. Okay, so that's what we're going to discuss now. So this is sort of step 2 in our process. And this is defining a mean stress. Mean as in like average, not like it's rawr mean. Okay. So for this, we're going to leverage the mean value theorem. I'm sure you guys all have the mean value theorem memorized, right? Right? Okay. If not, recall that on some function space, let's call this x and let's call this f of x. Just as a reminder, if you have some function that exists between what would be a and what would be b, and this function is all crazy and nonsensical, so on and so forth. Okay, here's your function, f of x, that there exists an average of that function between those 2 points. Let's try to sort of point it out here, is that the average of that particular guy is here. And this is what you might see as fx bar. This is the mean or the average of this function over the domain. And if we want to define mathematically what that is, then the mean value says that the average of this, which is fx bar, is normalized by the domain b minus a. 1 over b minus a is the integral from a to b of our general function f of x dx. All right, so this is the mean value theorem. It gives us an approximation for all points on that function over the domain from a to b. All right, now why is this useful for us? Well, this is useful for us because with our composite, we have a very strange function of the stress that is existing between the bottom of our laminate and the top of our laminate. And that's because we know the stress distribution changes as we move through the individual layers of the laminate. So we need some sort of average stress that encompasses the contributions of each one of the individual layers as we move through the layers to go from the bottom of the to the top of the laminate. So I'll put that sort of in words here, is that we will use this to describe an average stress that develops in the laminate as we move through the thickness. Okay, and so instead of trying to sort of sketch it myself, I'm going to actually bring in a picture here to help sort of describe what I generally mean. Okay. So we've seen this picture a couple of times now, and I just want to bring it back and talk through it. All right. And we'll also write here the general mean stress that we're going to calculate. All right. So remember, if we have a laminate with, let's say, layers 1, 2, 3, and 4, we have a strain that's applied to this guy, which is continuous through the thickness. Okay. There's no strain discontinuities. Otherwise, we'd have, holes in our piece. And we know that the relative moduli of each one of those layers could be different, which results in a stress variation through the laminate. Okay, different layers have different stresses in them, and there's maybe these discrete jumps that exist between the individual layers. So when I'm talking about using the mean value theorem, I'm talking about calculating what would sort of be like this average stress, sigma x, which kind of like encompasses the approximate average of all of these individual pieces sort of added together to give me sort of a mean value for that particular stress. All right. Mathematically, we would write that the mean stress in X is equal to the average over the domain of interest. So for us here, that is from the bottom to the top. So from negative h on 2 to h on 2, or if you kind of do the math, this will be from 1 on h of the integral from negative h on 2, the bottom of our domain, to h on 2 of the stress distribution that exists in the sky, sigma x, and I'm integrating over the variable z. All right, so this is the mean value theorem leveraged for this particular laminate to give us an average value of the stress that exists in the x direction of the laminate, given the various stresses of the individual layers of the piece. Right? So this is what we're going to kind of work through. All right, so let's look at this a little bit closely, and let's recall definition of nx, which remember was our sort of load applied per length, where here this is the force in the x direction normalized by the length of the laminate in the y direction. So you can go back to lecture number 1, slide 11, if you want to sort of get a refresher for what this actually is. And for us, we define this as the integral from negative h on 2 to h on 2 of the stress in x integrated over z. All right. So the force that is applied on the laminate must be balanced with the stress that is in that laminate as well. This is sort of an equilibrium relationship. Okay, so this is sort of an equilibrium. Okay, so this relationship here is sort of an equilibrium relationship. The forces and the stresses must more or less be balanced. All right, so we'll notice here that this particular integral looks very similar to the integral that we have when we're looking at the mean value theorem. The only difference is this normalizing term, which is this 1 on h. Okay, so we can conclude then our mean stress is the loads that we applied normalized by this value h. So that is, we have our sigma bar h is nx on h, very simply. Right? Similarly, we have that the mean stress in y would be ny on h, and the mean stress in s, or what we might see as tau xy, is going to be ns on h. Okay. Therefore, we can express sort of the average stress on the laminate in terms of the load that we applied by sort of taking the loads that we apply and normalizing by the thickness of the piece. And so we might consider writing this in matrix form. E, the mean stress in x, the mean stress in y, and the mean stress of shear, tau xy, going to be equal to the vector of loads that we apply, nx, ny, ns, all times 1 on the thickness of the laminate, h. I mean, this sort of makes sense physically when you think about it. This nx, ny, ns, this is the force normalized by the width of the laminate, more or less. And then if we do one more normalization, which is the thickness of the laminate, this is more or less like the stress is equal to force divided by the area. Okay? So you can think of it like that. All right, the inversion is something like, not really the inversion, but just sort of reorganizing, is that the loads that we apply are equal to the stress on the laminate, sigma x, sigma y, these mean stresses, all multiplied by h. Right? So these two guys they're probably box worthy. I don't know if they're sparkle worthy, but they're box worthy. Okay, so those guys get boxes. If you want to put some sparkles on them, that's up to you. Okay, this is where my madness takes over. But I don't think they're sparkle worthy. There are better equations. Okay, so that'll be it for today. We'll stop here. Then we'll talk about how we relate these mean stresses that we sort of just showed here to the strains that we're sort of developing using the inverted stiffness matrix. Okay, so that'll be it for today. Thanks for coming. I'll stick around for a few minutes if people have questions. Thanks. You're doing great riveting stuff here. I know. It's exciting. I'm trying my best.